Hi friends, in this one I'm going to take a look at the world of series and calculus and complex numbers, and we'll see what the connection is that we can discover there. So we begin with the following here. Imagine you're going to do 1 over 1 minus x. So again, this kind of presumes that you have studied the series a little bit already, okay? If you graph this, take a look. Then you have the following over here. 1 over and then 1 minus x. So when you graph it, you see that at x equals positive 1, there is what we call a vertical asymptote in this function. So naturally, in other words, if you try to find this, 1 over 1 minus 1, replacing x with 1, you find it's 1 over 1 minus 1, which is 0, and this kind of quantity is then called undefined. So that makes sense. If you try to represent this with a series, then it looks like this. Take a look. You're going to have 1 over 1 minus x, and then you're going to do summation as n goes from 0 to positive infinity, and then this becomes x raised to the n. Look at what happens if you try to evaluate the series at x equals 1, positive. When you do that, you're going to have the summation as n goes from 0 to positive infinity, and you're going to have here 1 to the n, replacing x with 1. When you write that out, it's going to be 1 plus 1 plus 1 plus ... You're going to just add up infinitely many ones. So of course, this would just become infinity. It would diverge. So we understand why, for example, at positive 1, the series here would diverge. Because in the function at positive 1, there's a lack of definition. 1 over 0 is not defined. So the two kind of fit together very nicely. But now look at this next weird thing that happens that is not obvious really. Imagine we have not just 1 over 1 minus x, but instead we take a look at 1 over 1 plus x squared this way. This is different. So imagine, let's do a graph of this function here. So when I do that, it's going to be the following. 1 over and then 1 plus x squared. It looks very smooth, it's continuous, there are no breaks of the kind that you see in the graph on the left side. So, let's see what happens. If you plug in x equals positive 1, you would have 1 over 1 plus 1 squared, which is then 1 over 1 plus 1, which is 1/2, no problem, it's a well-defined value. 1 goes in, 1/2 comes out. If you plug in negative 1, you would have 1 over 1 plus negative 1 squared. Again, when you square something, it gets rid of the negatives. You'd have 1 over 1 plus 1, which is 1 over 2. Well-defined value, no problem of any kind. In other words, if you look at this graph over here, what I'm going to do is the following. Let me stretch it out this way. Stretch it out a little bit more this way. You see, there are no issues of the kind that you see in the graph on the left side. In other words, when negative 1 goes in, 1/2 comes out. When positive 1 goes in, 1/2 comes out. How do we now construct a series representation for 1 over 1 plus x squared? And does something happen? It's kind of interesting along the way. Take a look. You can adapt 1 over 1 minus x as follows. You're going to put 1 over 1 plus x squared. This is the same as 1 over 1 minus negative x squared, because the two negatives give back a positive. Now, it's going to be the following in terms of a series. Summation as n goes from 0 to positive infinity. And here you're going to put negative x squared, this whole thing raised to the n this way. From here, let's find the interval of convergence. And remember that the function, the original 1 over 1 plus x squared, has no apparent issues. So now let's check the convergence of this using the ratio test. So that's the limit as n goes to positive infinity of the following. Negative x squared raised to the n plus 1 divided by just the original negative x squared raised to the n. Let's simplify this a little bit. You're supposed to do this in absolute value. The limit as n goes to positive infinity of the following. Negative x squared. You can break this up into an n part, and you can break it up into a negative x squared in the first part this way, because n plus 1 is what you see on the screen. And then from there, take a look at the next stage here. In the bottom, you still have that other part, negative x squared within parentheses to the n. What cancels and what remains? You're going to have the limit as n goes to positive infinity. The parts that are negative x squared to the n cancel off because they're the same. And all that remains in absolute value basically is just negative x squared this way. By the ratio test, this converges when this quantity, say, is less than 1. So in other words, look, it's going to be like this. An absolute value, negative x squared, has to be less than 1. However we choose to solve this, first of all, notice that when you apply absolute value, that negative that is attached to the x squared gets wiped away for the following reason, because you can break this up into two pieces that look like this, you see? And of course, the absolute value of negative 1 is 1, it goes away. And you just end up, therefore, with the following. Absolute value of x squared and then less than 1. Well, from here, when is this solved? This x squared is just a parabola, and when its values are less than 1, this is true for negative 1 less than x, less than positive 1. If you have trouble seeing that, just remember that x squared is a parabola. So when you graph it, this part, the absolute value of x squared, think about this. X squared is already a positive quantity. Doesn't matter what you plug in. When you square it, you make it positive, or it's 0, but that's it. Which means you don't need the absolute value bars. So as an intermediate step, what you could do here is the following. You could say, drop the absolute value bars and just write it this way, see? And then from there, solve that. If you have trouble understanding why it's from negative 1 to positive 1, graph this, take a look. The graph of x squared is this. This is a parabola, you see? What this is saying at this step right there, in red, let me kind of highlight this in red. What this is saying is, where is the parabola less than 1? When is that true? Well, look at the graph right here. You see this? That's true between negative 1 and positive 1. That's why here I wrote from negative 1 to positive 1. Let's stop for a second. Now, go back over here to 1 over 1 plus x squared. The function looks like this. It seems like there's no reason why the interval of convergence should begin at negative 1 and end at positive 1 and exclude the endpoints. At least no reason that is apparent from these operations. But is there a reason? There is one. The reason is hidden away in a complex plane. And we're going to make a complex plane graph. So I'm going to kind of put that right here. Now remember, in a complex plane, something happens that's different. In a complex plane, the horizontal axis is called the real axis. So in other words, you can still call it x right here, okay? And the vertical axis is called the imaginary axis. Often we kind of indicate it with IM for imaginary, like this. That's what it looks like. And now within here, I'm going to draw a circle. Alright, so I'm going to center it right here. Look carefully. And let's draw a circle. So when I do that, you see it's going to bring you out to this way. Now something happens in the circle. Remember, this here is 1. So that's the same as the 1 that you see in this position in the graph on the left side, right? And this is negative 1. So that's the same as the negative 1 that you see right here, okay? There's also a couple other values here. There's positive I, because we're in the complex plane. There's positive I up here. And there's also negative I down below, right here. These are the values that cause the issues with this function 1 over 1 plus x squared. What do I mean by that? If you plug them in, you have to remember something about complex numbers now. I squared is by definition negative 1. So now take a look at what happens. If I take this 1 over 1 plus x squared, but I plug in I, which is that value there from the top of the circle, I would have the following. 1 over 1 plus I squared. Well, that's 1 over I squared is negative 1. So it's going to be 1 minus 1, which is infinity. Right? Same thing with the other one. Take a look. If you have 1 over 1 minus, so replacing now I with negative I, it would be 1 plus negative I squared this way. Once you work this out, you'll end up with the same thing of basically infinity. This also explains the origin of the phrase radius of convergence. Radius of convergence is the distance to the nearest singularity. Where is the singularity located? It doesn't have to be located in the xy plane. That singularity can be located in the complex plane, at I or negative I, for example. And then the radius of convergence, the word radius becomes obvious because you have a circle, and the radius is this quantity right here, see? It really is a real radius in that case. Lastly, we should observe that we cannot use any value that lies along the ring. So for that reason, what you have to do really is take this thing and then just dash it this way. This also explains, friends, why now the interval is from -1 to 1. If you look very carefully here, you see the radius of convergence is 1, and it's generated by I and -I, and then any value that you pick out of here, you see, as you move this way, it encounters 1 right here, because the radius of convergence is 1, and I itself cannot be included, and that means if you go down to 1, the 1 itself cannot be included. And if you go over to -I, that looks like this, and then you go over here to -1, and you see the -1 itself cannot be included. So the reason for the lack of convergence, for example, at -1 and +1 is not apparent from the middle graph. But once you transition into the world of complex numbers and you discover I and -I is causing the issues, then that tells you about what's happening here also, right there. That limit in terms of being from -1 to +1 is coming from the world of complex numbers. But that's it. So thank you, friends. I'll see you in the next video. Please leave a like and subscribe.